Okay, welcome lecture number 38. In this lecture, we will solve one sample problem from the previous concept of maximum principal stresses and maximum shear stress. And later we will discuss about Mohr circle. Okay, um, major will be we cover Mohr circle for plane stress case. First, using this sample problem from the previous concept, a single horizontal force P, a 150 pound magnitude is applied at ND. So we have a force at ND acting over here. So we have to determine the normal and shearing stress on element at point H, having side parallel to x-axis and y-axis. So we have to find what will be the normal stress and shearing stress on this point H due to this load P, and parallel to x-axis and y-axis. So we have taken element over here and we have to find what is the stresses along parallel to that x-axis and y-axis on that surface point H. And part B, we have to find the principal planes and principal stress at point H. So first we will be finding the stress over here. So let me change the color to further clarify. So we take an element. So this side will be parallel to x-axis and this side will be parallel to y-axis. So we take an element, a small element over there, and we will find the stresses. So first what we will do, we take a section at H, at this H, and we will transform this force to the equivalent force moment system at the centroid of this section. And the radius, it's a circular cross section as shown over here. So it's diameter is 1.2 inch and the other dimension is given. And then we will find the normal and we will see what forces are there. So there will be one transverse force P, a shear force P, then there will be a bending moment M, and that bending moment will be due to P multiplied by 10 inch, and there will be a torsion as well, that will be P multiplied by 18 inch. So we have stresses due to bending moment, due to torsion load, and due to shear force. Let's see what type of stresses will be there. Okay, first we will determine an equivalent force couple system at the center of the transverse section passing through H. Then we evaluate normal and shearing stress at H, part A. Later we will find the principal planes and calculate the principal stresses. Now if you look at the direction as well, so we have a moment that is equal to 50 pound multiplied by 10 inch, 1.5 kilo pound inch, and it will be acting if you take right hand thumb rule. So if I'm looking from here, it is acting clockwise direction, and we have a torsion, and we have a shear force acting over here. Now this bending moment will cause bending stress, and that will be equal to sigma mc over I at H, and that this shear will produce shear stress, this torsion load, and we know that Tc by J. Now at point H, the force due to 150 pound will be shear force. This is a shear force will be 0. Why? Because the point H is at the top surface, and at the top and bottom surface the shear stress due to transverse load is 0. Okay, but if this point is somewhere here or here or at, then in that case we cannot ignore the shear stresses due to this force P. Okay, now we know the forces. Now we will calculate the normal stress and the shear stress. The normal stress obviously is the mx, so normal stress will be along the axis of the shaft, so sigma y. So sigma y will be mc over I. We know the value of moment c, 1 point, the total diameter was equal to 1.2 inch. So radius is 0.6 inch, and the distance will also equal to radius, because if you draw, so if you look at the circular cross section, so this is point H and this is my center, so this distance is 0.6. Value of I 1 by 4, pi r 4. So for the circular, so it is pi by 4 c4, and J, polar momentum inertia, was pi by 2 c4. So putting the value, so sigma x, obviously there is no normal stress acting on a x direction, so sigma x is 0. Sigma y we calculated, that is 8.84 ksi, and tau y is 7.96 ksi. So now if there is some other force that cause normal stress along x-axis, then we will calculate that also. So we have then, and there is no stress acting along z-axis, normal to the z-axis. So this element at h, so we take this element on the h. So these the force, the stress distribution is like this. One more thing, when two normal stresses due to loading condition, there is a two normal stress acting on the same axis, then it will add. Normal stress acting in same direction will add to the normal stress, other normal stress acting in same direction. Okay, and and same as a shear stress, but normal stress will not add with the shear stress. Okay, because the stress natures are different. Okay, now let's see how to find. Now part B, we know the stresses, sigma x, sigma y we know, sigma x is 0, and tau xy is known. So using the principal planes, tan 2 theta p is equal to 2 times tau xy divided by sigma x minus sigma y. Putting the value, tan 2 theta p is 1.8 and theta p is minus 30.5 degree, and the other angle will be 60 degree. So this angle from the original is minus 30.5 degree, means negative sign means clockwise direction. Similarly, sigma maximum and minimum is sigma x plus sigma y divided by 2 plus minus under root sigma x minus sigma y square plus tau xy square. Putting the value, so maximum will be 13.2 ksi and minimum is minus 4.68 ksi. So, and the sigma max will be corresponding to this y, sigma y, and sigma minimum is over here, and it's compressive in nature. Okay, these are the maximum normal and minimum normal stress on that point H. And if it's a brittle material, then we have to consider this sigma maximum. If it's a ductile material, then we have to calculate maximum shear stress. Okay, let's see. Mohr circle for plane stress. We already know the transformation equation can be represented as a equation of circle, and using that equation of circle, we can draw a circle to representing the stresses by taking y-axis as a tau axis and sigma axis as a x-axis. Sigma will be with respect to x-axis, this vertical axis, horizontal axis, and shear stress will be with respect to vertical axis. And this method was first introduced by German scientist or civil engineer Otto Mohr, and he was a German civil engineer, and he introduced this method when there was no computational power to find the stresses as different orientation. So he introduced this method, and that's why it's called Mohr circle. And now, right now, we are considering for the plane stress case, or you can say 2D case. So this Mohr circle will for the plane stress, will give you some simple geometric consideration to find or to get the critical values. That can be a maximum shear stress, that can be a principal stresses, using graphically, or we can calculating with the circle as well. So we know that plane stress rate, so sigma x and sigma y and tau xy will be non-zero, and the zero stresses is tau xy, sorry, tau xz, sigma z, tau xz, and tau yz is equal to 0. So this is the plane stress. And with the circ equation, the center is at average. So we know that the equation of the circle was sigma uh, minus sigma average square plus tau square is equal to r square. So this was the equation, circle of equation, where sigma average is sigma x plus sigma y divided by 2, and radius is sigma x minus sigma y divided by 2 whole square plus tau square. So using some, if we take some graph paper, so C location will be at sigma average, right? And the radius, and with that circle, center and radius, we can draw circle. Now, this circle, um, the stresses will be represented like this. So sigma x and sigma y, right? And this tau xy with respect to x-axis is showing in counterclockwise direction, right? And with respect to sigma y, this value is trying to rotate in clockwise direction. Now, the sigma x we will take positive, and tau xy we will take negative. Okay, but for the tau xy and sigma y, so tau xy is rotating clockwise direction, so we will take positive, and sigma y is again here positive. So this x and y point are representing the stresses, state of stress as shown over here. Okay. Now, if I rotate this line with angle 2 theta p, or this angle, that will be equal to 2 theta p, so this will give me the location, and it will coincide with the line AB. Now this point A and B are my principal stresses. So my principal stresses will be simply what? Sigma max minus sigma minimum. Sigma max, sigma minimum, sorry, it will be sigma average plus minus radius, because if you look this distance is sigma average plus radius minus radius. So that will give me the maximum and minimum value, and those are my principal stresses. By simply drawing it, the circle, I can find what will be the value of principal stresses. Similarly, if I can find this angle theta, I know this distance, right? And I know uh, this height, that is sigma x. So by using trigonometric ratio, I can find what is this angle, or I can apply this equation as shown over here. Now the direction of rotation of OX and OA is same as CX. Means if you look at this, this black line is representing the state of stress, right? That is this state of stress. Now if I rotate this line counterclockwise direction, so it will give me the principal stresses, and that angle will be where the principal planes are. And if I rotate this element with angle theta p, and again at the counterclockwise, so same direction over here and here, so this will give me the orientation of principal planes and also principal stresses, give me the principal stresses. Now on Mohr circle, the angle will be 2p. If you remember, the equation contained 2 theta, and from which we derive, in actual it will be theta p. Okay. Now Using that Mohr circle, we can find the stresses on different orientation. For example, the sigma x y as xy, that was the original orientation. Now I'm interested what will be the stresses if I rotate the element with angle theta. So what I will do, I will draw a line passing through the center and it will making angle 2 theta with respect to this xy. Now these points on the radius circumference, circle circumference will give me the value of stresses. So it will be tau sigma x prime and tau xy prime, and similarly over here sigma y prime and tau xy prime. So tau value will be equal, but the sigma value will change. Now if I'm interested that if I want to rotate the element, let's suppose counterclockwise theta prime, so what I will do, I will rotate this line and draw another line, and this angle will be 2 theta prime, and these value I can find the value on the these value will give me the state of stress at that orientation. So just showing therefore state of stress at angle theta with respect to xy axis. Construct a new direction x prime y prime at an angle 2 theta with respect to xy. Okay, and then we can find the stresses accordingly. So normal and shear stress are obtained from coordinates of x prime and y prime. Now, why this most plane circle is important or significant? For example, let's go back to the chapter 2 where we discuss uh, stresses due to axial loading. Suppose we remember with the axial load P and P prime as P prime and the cross section area is A. So let's consider this element, small element. So this element we have stress sigma x P by A where sigma y and tau xy will be 0, right? This element, this side is parallel to edge and this is parallel to this edge. Okay, now we know the equation for the circle that was equal to sigma x prime minus sigma average principal stresses. We know that sigma max and minimum is equal to sigma average plus minus radius, and sigma average we know that is equal to sigma x plus sigma y divided by 2, and the radius is equal to under root sigma x minus sigma y divided by 2 square plus tau xy square. Now in this case we have sigma x is P by A, but sigma y and tau y is 0. So average will be simply what? Sigma x by 2, right? And the radius will be equal to again sigma x. So, sorry, sigma x by 2. So this sigma x is now my principal stress. And if I draw a circle, the center will be what? Sigma x by 2. Radius is sigma x by 2. So if I draw it, so this is my circle. So x that will be equal to P by A. Now, maximum shear stress will be at D, obviously. Over here, we have maximum shear stress value, and that is equal to what? Half the value that is equal to the radius P by 2A or sigma x by 2, right? So at now this angle is how much? This angle is 90 degree. So in actual it will be 45 degree. Now if you remember when we discussed in chapter 2 stress on oblique plane, So maximum shear stress occur at 45 degree and it was half of the normal stress P by A, this one. So Mohr circle for this problem is like this, and it will give us, and this value is equal to radius, and radius if we calculate, so say that will be P by 2A. And if we talk about ductile material, obviously it will break under shear. So at 45-degree plane it will break, and usually cup and cone depending on the dimension 45 degree. But if we talk about brittle material, so it break at where you have maximum principal stresses. So and then perpendicular to the axis, and it will break something from this axis where you have maximum sigma x. Now, if you remember for the torsion loading, so that torsion loading, the element was under pure shear, means sigma x is 0, sigma y is 0. So tau xy is simply Tc by j, means this element is under pure shear. And the breakage of ductile material will be perpendicular to the axis. Now if I draw the average stress, what is average stress? Average stress is 0. So in this case, sigma average is 0. And radius of the circle is simply is equal to tau xy. So if you draw a circle, the center will be at 0, and this will be your circle with the radius is equal to Tc by j. Now, maximum principal stress where you have no shear will be at, again if you rotate this element 45 degree, in Mohr circle it will be 90 degree. If you rotate 45 degree, over there you will have maximum and minimum normal stress. The magnitude will be equal because this CA and CB distance is same, right? And the value will be equal to radius, that is equal to Tc by j. But the maximum will be tensile in nature and the minimum will be compressive in nature. So by sketching the Mohr circle, we get an idea of the nature of principal stresses and what will be the shear stress, maximum shear stress, and where will the orientation. So that's why uh, um, it's better to sketch the Mohr circle, but since now the computational power is too strong, so usually this method is rarely used in practice these days. Okay, let's see a sample application problem. So the state of stress is given. For the state of plane stress shown, A, construct Mohr circle, determine the principal planes. Part D and part C, we have two principal stresses. And part D, the maximum shearing stress and corresponding normal stress. So the state of stress is given. So if I want to write, so sigma x will be 50 megapascal. Tau xy, I can write 40 megapascal. And sigma y will be simply minus 10 megapascal. So taking this as my x-axis, and the top one will be my y-axis. Okay. So first what we will do, we will find the average stress and the radius, and we draw the Mohr circle. So the average stress is simply sigma x plus sigma y divided by 250 plus the negative sign you have to take for the compressive divided by 2, it will be 20 megapascal. Means if I construct it, so at 20 unit, my center of the circle will be there. And the radius, so for the radius, it will be what? Sigma x y, sigma x minus sigma y. So radius, if I want to write the radius, so let me change the color. So radius will be what? Sigma x minus sigma y divided by 2 square plus tau xy square under root. So sigma x minus sigma y, that will become 50 minus 10, 60 divided by 2, that will become 30, and tau xy is 40, so 40 square, so it will radius become 50. So you have a center, radius of 50, you will draw a circle. And this X point will giving me the stresses, and that will be equal to 50 megapascal and 40 megapascal. And this Y point will be giving me the stresses, that will be minus 10 and 40. Okay. Now, what will be the maximum and principal stresses? So this is, we construct a Mohr circle, and now we are interested what are the principal stresses. So it will be simply principal stresses will be OC plus CA. So this OA is total my maximum principal stress, that is sigma max, and that will be OA, and it will be OC plus CA. OA is equal to average stress, sorry, OC is my average stress, and CA is equal to radius. Now, average stress is 20, radius was 50, so maximum principal stress is 70 megapascal. Now, similarly, from minimum, not this is not maximum, this is minimum. So sigma minimum will be what? From this center to this. So what is this? So OB is my minimum stress. So that is equal to what? Radius from CB is my radius, or BC is my radius, minus this average stress. So CB or BC is my radius, and OC is my average. So if I minus it, so that will become minus 30 megapascal. Means sigma B is my minimum stress, and that value is minus 30. Okay, megapascal. So these are my maximum and minimum normal stresses on that axis. Now to find the what will be the angle. So I am interested to find this angle. So this is tan to 2 theta p. So that is simply what equal to CF. Sorry, tan 2 theta p will be equal to fx divided by CF, not CP. That is CF. So fx, if I want this location, if you remember, the x point location was what? X point was equal to 50 and minus 40. Now this distance is minus 40. And CF, what is CF? CF is simply what? OF minus OC. OF is 50. CF is simply what? OF minus OC. OF was 50 and average stress was 20. So that CF value is 30 megapascal. So when we put the value 40 by 30 to 2 theta p, so theta p is 26.6 degree, means this angle is 26.6 degree. But on Mohr circle it will be 2 theta p. Okay, so by using Mohr circle you can find the orientation of principal planes as well. Now the maximum shear stress and the corresponding normal stress. Okay, now for the maximum shear stress, where it will occur, obviously it will be occur on the this point D, where you have maximum value of tau. But if you look at this, this is equal to radius. So now tau max is my radius, so that is 50 megapascal. So now with respect to original, what is the orientation of the principal stresses? So it will be sigma p, because if you look at this, so this is my sigma p. In Mohr circle it will be 2p plus 90. In actual it will be p theta p plus 45 degree. On Mohr circle it will be, on Mohr circle with 2 theta s will be equal to 2 theta p plus 90 degree. But in actual, it will be like this. So if you put the value that theta p we already know, 45 degrees, so theta s will be 71.6 degree. Means from the original orientation, the maximum shear stress will be at this angle, and that is 71.6 degree. And the corresponding normal stress where you have maximum shear stress will be equal to average. Means if I want to write the coordinate of the point D, it will be what? Sigma average and radius and E as well. Now if I want to represent that element, so this was my original state. This is where we have maximum principal stresses, sigma max and sigma minimum, and this angle will be theta p. And at this orientation, means this is showing away from this original, but actually we are rotating this original one just to showing what is the nature, what is the value of stresses. That's why it's shown away from this. Actually we are rotating this element. Okay, so if we rotate this element with 71.6 degree, where we have maximum shear stress, that is equal to 50 megapascal, and the average stress will be 20 megapascal. So by using Mohr circle, you can find the stresses, nature of principal stresses, principal planes, and shear stresses, and you can also find stress at other orientation as well. So but this method is not used that very much these days, because we have a lot of computational power, we have different computational tools, and they give you quickly the value of principal stresses and maximum shear stress, where the principal stresses lie, the principal planes, and the stresses at other orientation as well. Okay, these are assignment problems related to section 7.2. So you have to draw more circle, so not draw it to the scale, but just draw it and find the values. I gave not that much problem. Okay, so less problem. And reading assignment related to section 7.2, please go through sample problem 7.2 and sample problem 7.3. So those problems will further clarify the concept of Mohr circle for you. So in next lecture, we will solve different problems related to section 7.1, and we will sketch obviously the Mohr circle as well. But we will solve few problems related to section 7.1, and obviously it will cover section 7.2 as well. Okay, thank you very much.